Welcome to this lecture in the ongoing series of lectures on real analysis. Today we'll be proving a very interesting theorem called the inverse function theorem. And last time so far what we did was, let me just recall the ingredients that we need for this lecture. So what we have seen much earlier in the course is this fact which says that suppose you have a continuous function defined on a closed interval, let's say, and you have another function such that the image of this function is contained in the domain of our previous function, so that you can compose the two functions, meaning this composite makes sense. And we have a point x0 in the domain of the second guy, such that, let's say, the limit of f at that when x approaches that point exists, and let us call that L. So it is some real number. And the continuity of the previous function then says that the value of g at L, because so for one thing that we should note is that L is actually lying in this guy, because the entirety of the image of f is lying here. So one can show, because this is a closed set, the limit is also lying in this set. So first of all, we should note that this is actually in the domain of g. So this makes sense. And the claim is that this is actually this number. So, well, that's not a claim because this is equal to L. The claim is this is equal to that. That is the claim. That you can sort of pull out the limit. But we have seen this because what we have seen is that if you have, let me write it here. So this thing we have seen is limit x tends to x naught g of f. So this is equal to g of L. This is what we've seen because g is continuous at L. For this fact to work, we just need the continuity of g at L and nothing else. And this is what we've seen in the lecture on composition of continuous functions or something. It was just after the algebra of continuity, I think. So this is how we stated it, but the way I want to state is, or rather note, is this, which is nothing different from saying that. It just looks a little bit nicer that you can sort of pull out the limit. So that is what I wanted to stress. And then we also discussed the invariance of domain. I don't know how many lectures back. So it says that suppose you have an injective function, injective continuous function defined on some interval I, then the image of f is also an interval. So that is what we stated as the invariance of domain. There may be other enunciations of this particular fact, but this is how I stated it. And one particular thing which perhaps I did not stress is this. So if you assume that I is an open interval, then the image is also an open interval. This is very easy to prove. Once you assume this much, then this is very easy to prove. And yes, we do need injectivity to make this claim. In general, it is not true that a continuous image of some interval is necessary, of some open interval is necessarily an open interval. That's not true. But for an injective continuous function defined on an open interval, the image is always an open interval. Okay, so this is what we'll use today. And we also proved Rolle's theorem. So I think the previous lecture was mean value theorem. And this is what we proved. So this says that suppose you have a continuous function defined on a closed interval a comma b, which is differentiable on this open interval, such that f takes the same value on the endpoints a and b. Then the claim is that the derivative of f must vanish at some point in this open interval. So that's Rolle's theorem, and the geometric meaning is very clear: is that the tangent must be horizontal at some point in this open interval. So that's Rolle's theorem, and now let us go to the material of this lecture. These are the problems. Okay. So first let me give a definition. We'll come to this figure, but first let us give a definition. So a function defined, let's say, on this open interval is said to be continuously differentiable if first of all it is differentiable, and the derivative function, which makes sense because we are assuming the function is differentiable. Once you have a differentiable function, you can form this new function, which is the derivative of the original function that you started with. So f is continuously differentiable if it is differentiable and the derivative is also a continuous function. Well, I shouldn't say also, but the derivative is a continuous function. Now, it may seem strange. Intuitively, maybe one would like to think that the derivative of a differentiable function better be continuous. It seems hard to cook up such examples where this does not happen, but this picture is where one such example is given, and let me get to that. So define a function from reals to reals by this recipe. So I haven't defined trigonometric functions, but just for the sake of this example, just to convince you that there do exist differentiable functions which are not continuously differentiable, I'll be using this function. You can easily get rid of this. You can easily cook up examples where you really don't need trigonometric functions, and you'll see once you understand this example, you'll see how to place something else here and still get a counterexample to the fact that every differentiable function is continuously differentiable. So we define a function like this, and just remember the picture of the sine function from high school, that the sine of x function looks like this. So that's all I'll use. Okay, so if you draw the picture of this guy, which takes the value 0 at 0, because you can't substitute 0 here, sine of infinity doesn't make any sense. So at 0 the function takes the value 0, and everywhere else just behaves like this. So it will, as if x is very, very large, then the magnitude of this thing can be very large, and so it can go arbitrarily high, and since this can take negative values, it can also go arbitrarily low, and as you come closer and closer to the origin, this magnitude will become smaller and smaller. So you'll see that the graph of the function is trapped between these two parabolas, which are just the curves of the square function and the negative of a square function. Okay, and now it should be obvious to you that the function is differentiable everywhere in the positive real line and everywhere in the negative real line, but I would like to also say that it is also differentiable at the origin. So why is that? So let us just use the geometric definition that we've seen. So to show differentiability, let me also say that actually the derivative is this, the tangent at the origin to this function is the horizontal line. So to show that, what we need to do is whenever we draw an epsilon cone, fix an epsilon and draw an epsilon cone, meaning the slope of this above blue line is epsilon and the below blue line is minus epsilon. We want to show that there is a delta greater than 0, such that whenever we pick a point in this delta neighborhood, right delta neighborhood, then the corresponding point on the graph of the function is within that cone, and that is simply because the square function is differentiable. So some part of the square function is within this epsilon cone. There is a delta greater than 0 such that the graph of the square function corresponding to this right delta neighborhood is within this epsilon cone. The same delta works for this lower the negative square function, and therefore since the above and the below are trapped in this epsilon cone for some small enough delta, the graph of f is also trapped in this epsilon cone, because the graph of the function is trapped between these two things. So therefore the right derivative exists, and it is the tangent is actually this guy, and similarly the left derivative exists and the tangent is this guy, but these two things form a single line. So the derivative in fact exists at the origin, and it is 0. So the derivative not just exists, but it is 0 at the origin. Okay, but what about the derivative of so we record this, and what about the derivative of f everywhere else? To do that, to see that, what happens to that, you'll see that if you, let's say, pick this point, then the derivative is very big. Similarly, this point, the derivative is very big. This point, the derivative is very big. So you can find a sequence of points converging to the origin such that the derivative is very, very big. If f prime were continuous, this couldn't have happened, because then f prime of some suitable sequence, this is not converging to 0, while it should have. If f prime were continuous, then this must have converged to f prime of 0, which is 0. But since this does not happen, as we saw, there is a sequence where this does not happen. These derivatives are very, very big. So f prime is not continuous. So this is an example of a function which is differentiable everywhere, but its derivative is not continuous. So this is a stronger condition than just asking for differentiability. A continuously differentiable function is better than a differentiable function. Okay, and now we can state and prove the inverse function theorem. It is a very beautiful theorem. So we start with a continuously differentiable function defined on an open interval. And suppose there is a point in this open interval where the derivative does not vanish. So then we claim then there is a neighborhood u of x naught with u contained in a comma b such that fu is an open set second is that f from u to fu is a bijection, which is as good as saying that f restricted to u is injective. And third is that the inverse function from fu to u is continuously differentiable. Now I should, instead of writing this, I should really write f restricted to u and then this, but I won't do it. I hope it is understood. Further, the derivative of f inverse at fx naught is given by this formula. So it's very easy to compute the derivative of the inverse once you know the derivative of the parent function. Here is the proof, and assume without loss of generality that f prime x naught is greater than 0, because the other case where f prime x naught is less than 0 is exactly similar to this, so I will be doing just that. Okay, so since this is continuous, since f prime, the derivative of f is continuous by the assumption that f is continuously differentiable, since this is continuous, there is an alpha greater than 0 such that this open set, this open interval, which I will denote by u, so we have defined u, has the property that first of all it is contained in a comma b, and the derivative does not vanish, or rather it remains positive for all x in this interval. And that is simply because of the continuity of f prime. If you have a continuous function which takes positive value at one point, then it takes positive values in an entire neighborhood. So that's all that we are using. Okay, so we claim that f restricted to u is a function from u to r is injective. Okay, so let's see. So if so suppose not, then there exist 2 points which let me use x1 and x2 to denote them. Then there exist x1 and x2 in u such that x1 is not equal to x2, but the values are same. This is what it means for the function to not be injective. But note that this is a differentiable function, or okay, maybe I'll say one more line. So but then the function, okay, so I'm assuming x1 is less than x2. Then the function, well, when I write this, I should really say f restricted to x1, x2, but I won't do it. It's just a notational mess. So, but then this function is differentiable with this being the case, and hence by Rolle's theorem, we have, or we, by Rolle's theorem, there exists some point in this open interval x1, x2, which is contained in u, such that f prime at that point vanishes, but this contradicts our choice of u, which is a contradiction. To the choice of u. We chose the interval u with the property that the derivative remains positive everywhere in that interval. So this claim is proven. This is indeed injective. And so, well, we've proven this thing. Now by invariance of domain, fu is also an open interval. Fu is an interval by the intermediate value theorem, but if you use the invariance of domain, which let me recall, it is here. So you just use the fact that this is also continuous. You will be able to show that actually this is an open interval. Or maybe otherwise also. So anyway, an injective continuous function on an open interval has its image also in open interval. This is very easy to prove. So now by invariance of domain, fu is also an open interval. Okay. So now we want to show, we will show that this is also continuously differentiable. Continuously differentiable. This will finish the proof. So first we'll show that this is actually differentiable. And from there it will fall out that if it is actually continuously differentiable. We will see how that goes. Is differentiable. So let y star be a point in f of u. And let me write f of u equals, maybe, I don't know what to use. Let's say, what's a good notation for an interval? I'll just use c comma d. And don't confuse this c with that c. There is, yeah, don't confuse these two c's. I'm just, since this is an open interval, I'm just writing it like this. Okay, so we have chosen y star here, and we will just show that f inverse is differentiable and y star. Let me draw a picture. This is not good. Okay, so let's say this is x naught minus alpha, and this is x naught plus alpha. This is c and this is d. And sorry, what is wrong with this? Yeah, that helps. That has to do. Okay, so we have this kind of a diagram, and I have some y star here, which, oh, this is very bad actually. Let me change it a little bit. And let me use this figure. So let me call this x star. So say we write x star to denote the inverse image of y star. Okay. Okay. So what we'll show is that, so we claim that the limit y going to y star of this ratio is this. And this will prove the differentiability of f inverse. Okay, so let's get started with that. So first, what we have is, we know that very much by definition that this is the derivative at x star. This is immediately by the definition of the derivative. And now note that since this guy is non-zero, and yeah, since this guy is non-zero, what we'll do is we consider the function which takes x to 1 upon x. So we consider that function, and since this is positive and therefore it is lying in the domain of that guy, what we have is well, so first of all, this is also a continuous function. So what we have is that g of the limit is equal to limit x tends to x star g of. Now there's a slight issue with writing this. What is the issue? For this to make for this to make sense, first we need to also show that this quantity is always in the domain of G, meaning it is always positive. But here is where we will use the mean value theorem, the Lagrange's mean value theorem. I did not recall it, but well, I'm sure you recollect anyway. So this is equal to the derivative of f at some point strictly between x and x star. But the derivative of f at any such point is greater than 0 because every point between x and x star is contained in the interval u. So that's that. Basically, x is in the, we're taking x only from this open interval. That's where we are taking x from. When you're taking limit, you can just consider the x's which are close to x star, and you can decide on the closeness. So I hope you follow that. So this is a correct statement now, and this is what I wrote here. This thing. So we have that, and therefore g of f prime of x star is limit x tends to x star which says that I am shuffling the two things. Okay, so once again, what have we done? We had this. For some reason we want this. We'll see why we want something like this. So we had this, and we note that if x is in a small enough neighborhood of x star, meaning in a neighborhood such that this neighborhood is contained in this neighborhood, then this ratio is always positive, because this ratio is equal to the derivative of f at a certain point in this neighborhood, but the derivative of f in this entire thing is positive, so at that point is also positive. So this always takes a positive value, and its limit is equal to that, which is also positive. So we can just hit both sides by the inverting function, this function, which we know is a continuous function, and hence we can just kind of pull out the limit. So once you pull out the limit, you get that, and then you do the basic, very simple algebra, and you will get this. So basically this is what I wanted to get, and you'll see why do I want to get that, and a hint is here anyway. Okay, so by therefore, so okay, fine. So we want to prove this. So I should have just written let epsilon greater than 0 here, and then proceed. So we want to prove this. We fix an epsilon greater than 0. We want to show that there is some delta greater than 0 such that whenever y is less than delta away from y star and not equal to y star, then this difference is controlled by epsilon. So that is what we want to show. So for that business we are doing it, and we'll see how it helps. So now since this is the case, there is some theta, thus there exists some theta greater than 0 such that whenever we choose x in the theta deleted neighborhood and x not equal to x star, we have x minus x star upon fx minus fx star this is controlled by epsilon. And yeah, one has to also say that this theta we are choosing small enough so that this theta neighborhood is contained in this thing. So that I will leave implicit. Okay. And now the invariance of domain, maybe I did not mention it, but the invariance of domain actually told us that this is continuous. This part was kind of obvious, that the image of an open interval under an injective function is an open interval. But the invariance of domain actually tells us that the inverse is continuous. So now, since f inverse is continuous at x star, at y star, we know that there is delta greater than 0 such that whenever we choose y in this delta neighborhood, well, deleted delta neighborhood, well, I don't need deleted delta neighborhood, just delta neighborhood, we have f inverse y minus f inverse y star is less than theta. So let me indicate that in the diagram. So I have some delta greater than 0. Oh, this is very bad. Yeah, this should be fine. Yeah, this is fine. So I have some delta greater than 0. So this is corresponding to y star minus delta, and that corresponds to y star plus delta. And with the property that this entire interval y star minus delta y star plus delta interval is mapped within the theta neighborhood of x star under the f inverse function. So let's say the theta neighborhood is like this. So this is x star minus theta, and this is x star plus theta. So there is such a delta simply because f inverse is continuous at y star. So now finally, if you choose y in this delta deleted neighborhood, then what we really care about is this estimate. Why do we care about that estimate? Because our claim is this. So that this is the estimate that we care about, and so then this is equal to x minus x star divided by f of x minus f of x star So I need to explain this. All I'm saying is, instead of y, write f of x. So there is some, once you fix a y in here wherever, there is a unique x which maps to that y under f, right? So I'm just saying, okay, so let me indicate that in the diagram. So I have some y All I'm saying is you go via f inverse and you'll get some, so there is some point x that you will get, and yeah, so I'm just calling x as the inverse image of y, and the point to be noted is that this x will be in this theta neighborhood of x star. In fact, the deleted theta neighborhood, this cannot be equal to x star. If y is not equal to y star, x cannot be equal to x star because of the injectivity. Okay. So therefore, since okay, so for some x in x star minus theta, okay, for some x with x minus x star less than theta and x not equal to x star. And when I write for some, well, it seems like it's some mysterious x. It's not some mysterious x. It is just f inverse of y. So we have that, but then the above thing is less than equal to, it's less than equal to epsilon, because we have that estimate here. We just use it here to get less than epsilon, not less than equal to, but less than epsilon. And that's it. So whenever we choose y in this deleted delta neighborhood, we see that this quantity is less than epsilon, and that's it. That proves differentiability. So therefore, the derivative of this at y star is this guy, which is nothing but that. But y star was arbitrary, so what we can say is that is the derivative of f inverse at any point y, well, I'll say more about that, is equal to that. And what is the more thing? For any y in f of u. So we have this, we have proven that. But now finally, since f inverse as well as f prime are continuous, and as well as this inverting function is continuous, we see that f prime inverse is also continuous. So by continuity of f inverse f prime and the function g that we wrote earlier, we see that f inverse prime is also continuous. Because f inverse prime is just a composite of three things. First you apply f inverse y, then you apply f prime, and then you apply this inverter. And composite of three continuous functions is continuous. So that's it. That is the last thing that we needed to prove in order to establish all of this. So it's a complicated looking proof, but it is not complicated. If you have followed the material prior to this lecture, this is kind of a very smooth proof. There's no very fundamentally new idea that we employed. Okay, so stay on this proof for as long as you need to in order to absorb it. But now let me just give two quick applications, or maybe just one quick application. So the lemma is, let f be defined from positive reals to reals as be defined as fx equals x to the n for all x where n is some positive integer, where n is some positive integer, then this function, which takes x to the nth root, the positive nth root, is continuously differentiable. It's not just differentiable, but continuously differentiable. So far we did not even know that such a thing is differentiable. So in particular, the square root function, if you take n equals 2, then this is the square root function. We did not so far discuss the differentiability of the square root function. But the inverse function theorem immediately tells you that it is indeed a differentiable function, because you can show that this is differentiable at every point of this guy. You can just immediately employ the inverse function theorem, because the derivative of f does not vanish anywhere. What is the derivative of f at any point? It is n x to the power n minus 1, and this is non-zero because x is non-zero. So this has non-zero derivative everywhere, and this is indeed a continuously differentiable function because its derivative is clearly continuous. This is again a continuous function. So it is a continuously differentiable function, and if you apply the inverse function theorem, you will be able to prove that this is also a continuous function. Sorry, this is also a continuously differentiable function. So in particular, a differentiable function. So that's very nice. And one particular concrete example I want to talk about is, let f be defined as this. Square root of x squared plus 5x, let's say. So then f is differentiable. Now doing this thing by hand, by going by first principles, taking those ratios like f of x minus f of x naught upon x minus x naught, I mean that way it will be a mess. But one just notes that I will write it sort of informally, that f is the composite of the square root function with this function, and if x is positive, this takes only positive values, so this composite makes sense. And this is of course a differentiable function, and this is differentiable as we just argued. So if you have a composite of two differentiable functions, then the function is also differentiable. Right, so the message that I want to get across is that when you are faced with proving differentiability of something, just try to break it down into composites and sums and products. It will be much easier to prove such things. One should avoid going via first principles in such cases. Okay, so that is all for this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.